Hi, everybody. We have next on the docket Volz, who is going to describe the work he did saving energy or potentially saving energy for the Bristol Myers squib in their condensate return. So it's been my pleasure to work with Lewis these last few years in lots of different capacities, and it's my great pleasure to introduce his final project here. So go ahead.
Thank you. Like he said, my senior design work has been on a steam condensate capture system at Bristol Myers, and like Zeke and Zach's project, it deals with energy, specifically conserving energy at the plant in Mount Vernon. Instead of electricity, they use natural gas to power their steam systems, and I'll talk about that a little bit more in my presentation. So first, a little bit of background about Bristol Myers. They are a pharmaceutical company, and their mission is to discover, develop, deliver innovative medicines that help patients prevail over serious diseases. And in Mount Vernon specifically, they develop tablets that are used in diabetes treatments. The Mount Vernon facility has research and development portion where they try to discover new drugs and determine the marketability of them. They also manufacture tablets, and they have warehouse and storage supply facilities. So, and also, I guess I'll bring your attention to this map. Here is USI on the map, and their facility is located about 10 miles west of USI, near Mount Vernon, Indiana. And zooming in on this facility, the manufacturing spaces are over in here, along with the warehousing spaces, and they've recently turned some of this warehouse space into new manufacturing suites, and that requires a new steam system to run these different manufacturing systems. And all of this is powered from a natural gas boiler over in the utility building. And to give you a little scale, there's about a half a mile distance in between those, so there's about a half a mile of steam pipe running between these two buildings. So I'll go into a little overview of the steam system. I can't show you their steam system because of security issues, but I can show you this block diagram that gives a general overview of how their system works. And first, before the water can be boiled, it must be purified with a water softener and deaerator to remove all of the entrained air. And all of those chemicals and air would tear up the boiler and the rest of the steam system. So after the water is purified, it's heated by natural gas in the boiler, and Bristol Myers system produces about 44,000 pounds per hour of steam on average. And then that steam is pushed through the distribution and piping system to the various process uses. And whenever the energy is pulled out of the steam system, condensate forms, so the steam condenses into water. And it's collected through steam traps and piped back. And it's supposed to be piped back to the boiler. Since the condensate is still at a high pressure, first it must enter these flash tanks. And a flash tank is a big metal tank where the steam pressure, or the condensate pressure is lowered. And in that process, a portion of that condensate flashes into steam and is vented to the atmosphere. And then the low pressure condensate is allowed to collect at the bottom of the tank and be returned to the boiler and reused. That eliminates the need to process more water. However, there's a certain percentage of that steam that's vented to the atmosphere, and that's what this project focuses on. This condensate water purification process costs money, and all of the vented steam that is being lost costs Bristol Myers money, and because they have to reheat the steam and they also have to process it. So this is a picture, the only picture that I have of the system, specifically these flash tanks. There's a high pressure flash tank, and then in the background a medium pressure flash tank. So there are two flash tanks that are exhausting the steam to the atmosphere. And Bristol Myers has noticed that their utility bills have not dropped like they had hoped, and they believe that this exhausted steam is the reason that their energy bills are higher than they had anticipated. So they asked me to take a look at how much steam is being exhausted to the atmosphere and come up with solutions to this problem. So the objective is to design a system that reduces the quantity of vented steam so that the treated water can be reheated by the boiler and so that the heat can be redirected to the current process. And in the block diagram, this system would capture this vent steam and return it to the boiler or return it somewhere else and close the loop of this system. The capture return system must reduce the steam vented to the atmosphere. It must be easy to maintain by either Bristol-Myers staff or an outside steam firm. And it must provide a return on investment by recovering that thermal energy and returning the condensate to the boiler. To find out how much condensate flash steam is being lost to the atmosphere, we have to calculate the vapor quality, which is that percentage of flash steam. And to do that, the state points on the vapor dome are found for the high pressure and medium pressure tanks. So the red here is the high pressure tank, and the orange here is the medium pressure. I may have said that wrong. I want to clarify that the red is the high pressure and the orange is the medium pressure. So to calculate this percentage, the enthalpy of these state points is plugged into the equation on the top right, and the vapor qualities, the percentages at the bottom, are the percentages by mass of condensate water that's being exhausted to the atmosphere. And again, this liquid is very valuable because of the need to replace it at the boiler and the need to reheat it. First, the need to replace the physical water. The water that needs to be replaced is called makeup water, and the cost of that are salt and water in the softening process, chemicals in the deaerator, and then the actual water from the utility that Bristol-Myers pays to the utility companies. And also, this water has to be reheated from 50 degrees to 212 degrees because that is the temperature that the condensate would be returning to the boiler if it were recovered. So the cost per 1,000 gallons of this water is $15. That compares to Evansville residential rates of about $5.75. So approximately 3 times the cost of the water that you buy from the Evansville utility. And the total cost of this makeup water on a yearly basis comes to about $25,000. And I calculated that by taking the flow rate of the high and medium pressure condensate lines and multiplying by that price per 1,000 gallons that I came up with. So the other portion of this energy is the thermal energy. And this is the energy that could be recovered by a heat exchanger if it pulled all of the heat out of this flash steam. And again, using the flow rates of the medium and high pressure lines, the portion of flash is found by multiplying the flow rate of the condensate times the vapor quality. And then the energy that could be recovered is the energy that is required to condense all of the steam in that flash steam to water. And that's represented by this lower equation. And the recoverable energy comes to a total of about 84,000 for the high pressure line and 16,000 for the medium pressure line. And to put these two makeup costs and recoverable thermal energy costs together, most of the money can be saved by recovering this thermal energy. But any system that recovers this thermal energy will also recover the water costs. So the total opportunity cost for this system is approximately $125,000. So now that I've told you that there is money that can be saved, I'll go into the options how to recover this flash steam and return the makeup water to the boiler. The first system is a cascade system. The second is a high pressure return system, which is a system that Bristol-Myers had someone design before they came and asked me for help with this project. And then the vent condenser heat exchanger is the third option, and the fourth is the subcool condensate heat exchanger. So first, the cascade system. The cascade system takes this vent steam from the original system and pipes, instead of piping the steam to the atmosphere, it would pipe it to a manufacturing use, a low pressure use somewhere else in the system. So in this case, I drew this line back into the distribution and piping system because it would be used in a low pressure use somewhere. However, Bristol-Myers is unable to find a low pressure use for this steam. Advantages of a cascade system are that it would feed the flash steam directly to the low pressure use and that only a few pipes and valves would need to be sized and installed. However, the manufacturing would have to be shut down for installation and there are not low pressure applications nearby. Also, there would still have to be low pressure steam applied to any process uses that were used because this low pressure steam is not a constant supply from the flash tanks. So the second system, a high pressure return system, removes the need for that flash tank over here in the manufacturing areas from the rest of the that you saw in the other plot diagrams, and moves that flash tank over to the utility building near the boilers. So the high pressure return keeps the condensate at a higher pressure instead of dropping it to a low pressure. This requires high pressure pumps, and it would require a half a mile of new condensate line, the distance between those two buildings. And then the flash steam is used in a cascade sort of system back in the utility building to power the de-aerator that's already in use in the utility building. So this system recovers the high pressure condensate and it also recovers the flash steam by using it in a cascade system. This cascade system was very expensive, and like I said before, Bristol-Myers had an estimate from an outside company, and they were unsure of the opportunity costs, so they asked me to analyze this system. The other options that I found were vent condenser, which is a heat exchanger that's placed in line between the flash tank and the vent to the atmosphere, and this uses cold water, cold process water, and heats it with the energy of flash steam. So this processed water would be used elsewhere in the manufacturing facility. And when this heat is extracted from the heat exchanger, all of the steam would condense to liquid and would drip out of the heat exchanger to the current return system and would return to the boiler. Good thing about this system is that it would continue to work even if this processed water wasn't added. It would still vent the steam as normal. And here's an example of a vent condenser that I found online. These devices are not very common in the area in steam systems. They're not used frequently. So the maintainability of this system is unknown for a processor like Bristol-Myers, and firms in the area don't typically deal with these. So maintaining this system could be difficult. The fourth system, a subcool heat exchanger, pulls this energy out of the condensate before the flash tanks. So again, it uses cold processed water and uses that hot water to preheat water for another use. And instead of pulling condensate out, it lowers the energy state of this condensate so that there is no flash steam. It reduces that vapor quality to zero, so the flash steam is eliminated. And again, it eliminates this vent steam. The fourth, here's an example of one of these heat exchangers. They're commonly used in industry. Again, it brings in the cold processed water, heats it with the high temperatures of the condensate water. The economics of these systems, there's a lot of numbers on here, so I'll try to draw your attention that the opportunity costs of the high pressure and cascade systems are higher than the heat exchanger systems because there's all of that processed water that's being pumped into the heat exchangers costs money and is going to be an operating cost that's accrued annually. And then the capital cost of the cascade and the high pressure systems are much higher than these heat exchanger systems because these heat exchangers are only about $7,000 a piece. And the reason that the vent condenser and subcooling heat exchanger are different is because in this system, two heat exchangers have to be used. Again, the economic analysis, the present worth of this high pressure system in 5 years is about 50,000, and the subcooled heat exchanger is much higher down here, around 200,000. Only at a 10-year period does the high pressure return system outweigh the subcooled heat exchanger. So we eliminated the cascade system because there are no low pressure uses nearby. The high pressure system is capital intensive. The vent condenser is not easily maintainable, so our option, or the option that I recommend is the subcooled heat exchanger, and that's in both of the condensate lines. So again, this project aims to reduce the natural gas and chemical inputs at Bristol Myers, and this is going to save them money, but it's also going to save energy, and that's part of the reason that I decided to come back to school and become an engineer. This is the type of project that I wanted to work on. So I'd like to acknowledge my family for encouraging me to come back to school and supporting me through my 4 years here, the engineering faculty for supporting me the whole time that I'm here, specifically Ms. Donna Moore for all the help she's given, Dr. Field, who's taught me 6 classes, and finally been my senior design advisor, Dr. Mitchell, for heading the department and doing all the tough tasks that he does, organizing everyone. And then finally, Michael Sherrard and Michael Fouquet from Bristol Myers for providing this project. I'll open it up to questions now. Thank you.
Questions? So Luis, what was the final recommendation here?
The final recommendation was the subcooled heat exchanger, the heat exchanger that pulls energy out before the flash tanks.
And could you show the block diagram of that?
Yeah. This heat exchanger is in the condensate line before the flash tanks. So it's not cooling the steam, it's cooling the high pressure condensate before the flash tank. And that lowers the energy state of that condensate and reduces the amount of flash steam theoretically to 0.
So I guess that was the question I asked you during the midterm review was, is Bristol Myers really needed that process water out there? Or how much of a demand is there for that?
How much of a demand is there?
Yes.
I asked Bristol Myers this question. They told me that they have found a use for this process water, but they have not specified how much water they can use.
Louis, great job. Thank you. Did you go back to the first diagram where you describe the steam process, please?
Yeah.
That one. Perhaps you mentioned that and I missed it, sorry. But what percent goes, to the atmosphere? Yeah.
In the high pressure, there's 2 different tanks, a medium pressure and a high pressure tank. In the medium pressure, it's 8% of that condensate escapes as flash steam, and then in the high pressure, it's 13%.
Okay.
On your alternatives, did you go as far as picking out a vendor and sizing the equipment?
I found this heat exchanger. I wasn't able to find specifics like the U value and whatnot to actually size this heat exchanger. I tried to contact the vendor, but they never got back to me. However, on the subcooled heat exchanger, I contacted Bell and Gossett, or Hydronic and Steam in Evansville, and talked to a salesperson there, and he gave me a few options, including this heat exchanger, and I did size to lower the temperature from 325 to 154 degrees Fahrenheit. There's 40 gallons of processed water that need to be used per minute, and yeah, I did find a supplier, but I didn't find someone to actually install the system.
Other questions? All right, let's give them a hand.